With this video, we're going to begin activity 14. This is about lesson 14-1, altitudes of triangle. Learning goals are to determine the point of concurrency of the altitudes of a triangle. That simply means where's the point where the altitudes intersect each other, and also to use the point of concurrency of the altitudes to solve problems. Activity 14 has this little story written in a poem form. Lucky Leon was an old gold miner whose hobby was mathematics. In his will, Leon left a parcel of land to be used as a nature preserve. The will included a map and the following clue to help find a buried treasure. At the point on this map where two altitudes cross, in a hole in the ground, some treasure was tossed. Stand at the place where two medians meet, and the rest of the treasure will be under your feet. Each locked in chest where they will stay until the time someone finds a way to open each lock with a combination using digits of the coordinates of each location. So you notice in this poem leading to the buried treasure, there are some vocabulary words, altitudes, and then later on medians, and these are the focus of this unit 14. Okay, we have Al, Jeff, and Cal, and they're going to design the layout of the nature preserve. They use the map to help with the design. The parcel is shaped like a triangle with two rivers and a lake bordering the three sides. So here we have this triangle piece of land that was willed for the nature center, and we have these rivers, and then we have this lake down here. In order to preserve the natural surroundings, Al, Jeff, and Cal want to build as few structures as possible. They decide that the design of the nature preserve will include a visitor center at each of the vertices of the triangle, so here, here, and here, a power station that is equidistant from the three visitor centers. So we have to have some mechanism of finding the point somewhere within the triangle piece of land that's the same distance from the three corners. And we also want to find a primitive campground inland equidistant from each shoreline. So if we think of the shorelines of the rivers as the sides of a triangle, we want to find a point somewhere in the triangle that's equidistant from the three sides. They also want to find the treasure. Al, Jeff, and Cal decide that their first priority is to find that treasure. They begin with the first clue from Leon's poem. At the point on this map where two altitudes cross, in a hole in the ground, some treasure was tossed. Since they do not know which two altitudes Leon meant, Jeff decides to place a grid over the map and draw all three altitudes to find the coordinates of any points of intersection. So here we see that. We have that triangular parcel of land, but rendered on a coordinate grid with the x-axis and the y-axis, and the vertices are located with the dots. Question 1. Determine the slopes of the three sides of triangle AGC. And this is shown in purple. So we have the slope, using the letter M for slope, of segment AG. The bottom of the triangle is horizontal. Its slope is 0. The slope of segment AC, so this one right here, is rising 24 units and running 12 units. 24 over 12 is equal to 2. Or we could have just noticed that with the marks, that it's counting up 2 units over 1 unit. Up 2 over 1. Up 2 over 1. The other side of the triangle, called CG, has a slope of -1. We can use the slope formula and subtract the ordered pairs, or simply observe that from this dot, we're going down 1 over 1, down 1 over 1, down 1 over 1. Number 2. Determine the slopes of the altitudes of the triangle. Well, we need to know what altitudes of a triangle are. Altitudes of a triangle are defined in this green box here on the side of the screen. An altitude is a segment from a vertex perpendicular to the opposite side of the triangle. That idea about being perpendicular will help us to answer number 2. When it says determine the slopes of the altitudes, these slopes will be perpendicular to the sides of the triangle that the altitude is being drawn towards. And we know that from an earlier lesson, perpendicular lines have slopes that are opposite reciprocals of each other. So question A, what is the slope of the altitude from A to CG? Looking up above, CG had a slope of -1. The opposite reciprocal of -1 is +1. Question B, what is the slope of the altitude from C to AG? So looking up above, AG was a horizontal line with a slope of 0. A line perpendicular to that would be vertical, and vertical lines have an undefined slope. And question C, what is the slope of the altitude from point G to segment AC? So looking up above, if the slope of AC was 2, then a line perpendicular to that would have an opposite reciprocal slope of 2. That would be negative, and then 1/2. The opposite means to change to negative. The reciprocal means to create the fraction 1/2. Justify your answer in every case. Our reason is this idea about being opposite reciprocals because of perpendicular. Now number 3, use each vertex with the corresponding slope to graph the 3 altitudes of the triangle in the grid. So this first one here, the one that goes from point A across to side CG with a slope of 1 will look like this. Up 1/1 here, up 1/1 here, here. We can keep doing the slope of 1 to very accurately draw this line in. It's going to touch right there. And so we can come back nice and slow and carefully, draw in that segment, touching that at a 90-degree angle. Okay, the question B1 here, the one that goes from the vertex C to side AG, it has an undefined slope, meaning it's perfectly vertical. So it's just going to drop straight down like this, trying to draw very slow and carefully, touch at a 90-degree angle. And finally, this other one, the one that goes from the corner G to segment AC, we found that it has a slope of -1/2. And so let's measure off that slope. From G, we can go up 1/2, up 1/2, up 1/2, up 1, left 2, up 1, left 2, and here, and here. And so it looks like this line is coming like this. And again, touches this side of the triangle at a 90-degree angle box. All right, we just did problem 3. Question 4, after drawing the altitudes, Jeff is surprised to see that all 3 altitudes meet at one point. What are the coordinates of the point of concurrency? Well, they look like they all meet right there. And that is at, let's see, this is counting by 2's across here, so that is at 12, 12. So the point of concurrency of the altitudes is 12, 12. For some reason, Al's not convinced that the altitudes of the triangle are concurrent, and he wants to use some algebra to determine the coordinates of the points of intersection of the altitudes. I guess he doesn't believe the accuracy of our drawing that it really is 12, 12. So number 5, to use algebra to find the point where the altitudes meet, we need to know the equations of the altitudes. Question A, state the coordinates of one point on the altitude from A to CG. So looking at the picture, the altitude from A to CG, one of the points along that is the point 0, 0. Recall that that altitude had a slope of 1. So in question B, we can write its equation. Because we have a point and a slope, let's use point-slope form. Y minus the y coordinate of a point on the line is equal to m times x minus the x coordinate of a point on the line. We can simplify this to create y equals 1x, or simply y equals x. Question C, write the equation of the altitude from C to AG. So that's this one here running down vertically. One of the points for sure on that altitude is 12, 24, and recall that it was a vertical line. And so vertical lines have the equation x equal, and then it was x equals 12. If the point 12, 24 is on it, then x is equal to 12. Question D, write the equation of the other altitude. So one of the points that is for sure on this altitude is 36, 0, and that one had a slope of -1/2. So if we know that 36, 0 is on the line, and we know that its slope is -1/2, we can again use point slope form. Y minus the y coordinate of that point equals m times x minus the x coordinate of a point on the line. And then simplify this. Y equals -1/2 x plus 18. Question 6. Use the equations for the altitude from point A and the altitude from point C to determine the point of intersection and show your work. First altitude had the equation y equals x, and that other altitude had the equation x equals 12. I've put them together in what's called a system of equations. Hopefully you remember this topic from algebra. We can solve a system of equations to find their point of intersection by using substitution method or combination method. I'm going to choose substitution method. Because I know x is 12, then in this equation we can replace x with 12 and we get y equals 12. Notice how we know that x is 12, comma, and y is 12. 12, 12 is what we thought the point of intersection was. Number 7, let's verify that that point of intersection is also on the altitude from point G. The altitude line from point G had this equation. And if 12, 12 is on that line, then putting 12 in for y and 12 in for x has to satisfy the equation. Let's see if doing that checks out. -1/2 times 12 is -6, and -6 plus 18 does make 12. That checks. Number 8, explain why the algebra from items 6 and 7 demonstrates that the three altitudes are concurrent. It shows that 12, 12 is a point on all three altitude segments. So that convinces Al that the altitudes are concurrent for that particular triangle, but he's not convinced that altitudes are concurrent in every triangle. This question asks us to use geometry software to explore this idea. We're not going to take the time to do that, but if we do geometry software to quickly look at lots and lots of triangles and to look at their altitudes, we would find out that yes, the altitudes are always concurrent. And is the point of concurrency always inside the triangle? We would find out that that answer is no. Sometimes the three altitudes intersect each other at a point on the triangle or maybe even outside of the triangle. Number 10, the first part of the buried treasure is located at the orthocenter of the triangle. Over here in the green box on the side, that's what you call the point of concurrency of the altitudes. The vocabulary term is the orthocenter, the point where the altitudes intersect. So the answer here, what are the coordinates of the location of the first part of the treasure? That would be the 12, 12 that we figured out. Here we have some check your understanding questions, so I'll pause the video. In this lesson, we determined the point of concurrency of the altitudes. This is actually called the orthocenter. We did this both by graphing and carefully drawing lines to see where they intersect, but we also did this using some algebra.